Today we're going to learn some techniques of differentiation so that we don't always have to go through that limit process using the definition of derivative. So the first one we're going to look at is the constant rule. And what this says is the derivative of a constant is zero. And we'll have the notation. This notation here means the derivative with respect to x is the dx of a constant, some constant is zero. And it makes sense because think about the graph of y equals a constant. You get a horizontal line, and we know that the slope of a horizontal line is always zero. And we know that the derivative is how we find the slope of the tangent line at a point. So for all these situations, and make sure you use correct notation. So if we say y equals 9, you have some options. You could say dy dx equals 0. I'm just going to use y prime equals 0. That's another notation for the derivative. So for part B, f of x equals 0. It's a constant, so f prime of x equals 0. S of t equals -8, which is a constant, so s prime of t equals 0. Y equals 1 over pi cubed, which is a constant, although sometimes this tricks people, but it is a constant, so we get y prime equals 0. So that's an easy one, so just remember the derivative of a constant is 0. So the next one, still pretty easy, the single variable rule, and this just says that the derivative, if you're taking the derivative with respect to x, of x, you get 1. And think about the line y equals x, how the slope is always 1 at any point on that line. So that would make sense. So if we go through here, then we have if y equals x, y prime equals 1. F of x equals x, f prime of x equals 1. S of t is t, so s prime of t is 1. And g of t is t, so we get g prime of t is 1. So functions for which the derivative exists are called differentiable. A function may be differentiable at some x values and not differentiable at others. I think I had kind of told you about like the absolute value graph. It's differentiable, but not at when there is a corner. So, and we're going to learn more about those coming up. So the next one up is the power rule. And this one we kind of talked a little bit about in class, how if you have a function, if you have some kind of a polynomial function, power function, then you can actually differentiate this using the power rule. And what you're going to notice is the power is going to drop down and be multiplied by the variable, and then you're going to reduce the power by 1. Now, it works for negative exponents, it works for rational exponents, so sometimes you have to change the format, so we'll see some of those. So for example, on this first part A, we would say y prime, so I'm going to have the 2 drops down times x, and I would reduce the power by 1, but I don't need it because it's just a 1. So here, if f of x is x to the 6th power, then we get f prime of x equals 6x, drop the power by 1. Here we're going to have s prime of t. We'll have 30t to the 29th power. Just be glad you don't have to do it with the limit statement. Can you imagine to the 30th power? That would take a long time. So on this one, we're going to rewrite this first. Y equals x to the 1/2 power. So you'll find that you're going to do that always for radical functions. And now we can apply the power rule. So we get y prime drops down, so 1/2 x, and then we're going to reduce this by 1, so then we'll get -1/2. It's all right to leave it like that, but if it's given to me in radical form, a lot of times I'll put it back in radical form, which tells me that this is a square root of x, but it's in the denominator. So that would be my y prime. Okay, I guess we also, it said here to determine any values of x for which the function is differentiable. So on parts A, B, and C, it's going to be differentiable everywhere because you have polynomial functions. They are smooth and continuous. There are no values that we exclude from the domain. For this last one, now we could say it's differentiable everywhere on the domain. We had something come up like that in class. or it's differentiable for values of x greater than 0 because we can't take the square root of a negative. So, but that would, greater than 0, well, this actually would be greater than or equal to 0 for the domain. But here, because it's in the denominator now, it would not be differentiable at 0 because my derivative is not, the domain does not include 0. Okay, so going on here in part E, if we change this to x to the minus 1, then I'm going to get y prime equals negative x to the minus 2. And I'm going to change that to negative 1 over x squared. Remember, when we have a negative exponent, it's going to flip to the denominator. So this one we're going to think of as x to the minus 3, which means f prime of x is negative 3x decreased by 1 makes this a minus 4, which gives me negative 3 over x to the 4th. Remember that 3 doesn't flip because it doesn't have the exponent attached to it. So here we're going to think of this as t to the negative 1/3. So we're going to get s prime of t equals negative 1/3. Subtract 1, you get negative 2/3. Okay, so if you wanted to switch this back, let me just show you. We're going to have, this is going to flip to the denominator. I'm also going to put it back in radical form. So I'm going to have negative 1 over 3, and this is going to be the cube root of t squared. Okay, I'm going to do like a little rewind here. You guys are probably sitting there thinking, what is she talking about? Okay, luckily I got this before I went too far on. Didn't want to start my video over again. Let's try that subtraction again. Subtracting 1, which would be 3/3, gives me negative 4/3. Okay, so if I want to leave this as a positive exponent, I'm going to change this. And I can just flip this and make it t to the 4/3. And I'm just going to leave it like that, but with a positive exponent. All right, moving on. Let's change this to x to the minus 3/4. So we get y prime equals negative 3/4 x, and we're going to subtract 1, so I'm subtracting 4/4, so we get negative 7/4. If I want to write that with a positive exponent, then I'm going to flip this to the denominator. Okay, now if we want to think about any values where the function is not differentiable, clearly x can't be 0 here. It's not going to be differentiable at 0. Same thing here, not differentiable at 0. Same thing here because it's not going to be differentiable at t equals 0. And for this one, because we have an even root, we have a restriction on the domain of this that x has to be greater than 0. So it wouldn't be differentiable if it was less than or equal to 0. So it is differentiable when x is greater than 0. So this next rule is the constant multiple rule. And this just says that if you have a constant times your function, the part that has the variable in it, that you can just take the constant times the derivative. So for example, if we switch this to 2x to the minus 2, I can think of this then as 2, if I want to find the derivative. So if I want to find, let me just use some notation. I'll show you what work I would really show. If I were going to find y prime, I'm going to take 2 times the derivative with respect to x of this function right here. So that's what that's saying. So then I would end up with 2 times negative 2x to the minus 3, which of course is just negative 4x to the minus 3. So when you do that, then here, let me just kind of show you this easier. On this one, the one that I just did, you would just use you'd have y prime equals, and you're just going to multiply the negative 2 times the 2, negative 4x to the minus 3. Just this is what you're doing. This is the rule. This is what we actually do. And so then we can just change that to negative 4 over x cubed, and we are good. So on this next one, let's rewrite this as 4/3 x cubed. So to get f prime of x, we're going to take 3 times the 4/3, so the 3's cancel. We're left with 4x squared. Next one, we don't really need to do much here. This is like having a -1, so 5 times a -1 is -5, t to the 4th power. And on this one, I'm going to write this as 4 times x to the 1/2. So then I get y prime equals half of 4 is 2. And when we subtract 1, we get -1/2. So using a positive exponent, I'm just going to change this, or you can even flip it back underneath, because that's pretty simple to put back in the denominator. Now, I do want to point out, notice my notations. So when you are writing this down, don't just write down 4x squared. It is f prime of x. So make sure that you are putting the proper notations on these problems. So on the next one, I'm going to write this as 5/3 x to the -3. So that's kind of my setup to use the power rule. So now I'm going to multiply, the 3's cancel, but I'm left with a -5 x to the -4. And then I'm just going to flip that back for my answer. Next one. Now, what I would do on this is actually evaluate this 3x quantity cubed. So when I do that, I get -5, cube the 3, we get 27x cubed. So now I'm still leaving this as f of x, and I'm going to think of this as -5/27 times x to the -3. Now I'm ready to find the derivative. So when I multiply, I'm going to have a 9 in the denominator. It's going to be a negative though, so it's going to be 5/9 x to the -4. And then we can flip that back, so we get 5/9x to the 4th. Okay, next one, I'm going to change this to 40t to the -1/2 power. So s prime of t is going to be -20, because I'm taking half of 40, but it's a negative. T to the -3/2 when I lower that by 1. So then I'm going to get, I'm just going to leave it in fraction form, so change that to t to the 3/2 in the denominator. And on this one, I'm going to have 12 times x to the -5/3. Remember, power on the top, root on the bottom. It's negative because it's in the denominator. So then you're going to multiply -5/3 times 12 to get the derivative. And when we do that, we're going to get -20. Lower this by 1, which makes that by -8/3. So that's my derivative. I'm going to change that to -20 over 8. Oops. Make that an x. X to the 8/3. So the next one, the sum or difference rule, it's almost intuitive, and that just says that if you are taking the derivative of a sum or a difference, you just can add or subtract the derivative of the parts. So for example, here I have 3 pieces. I have x squared, I have 5x, which remember is our single variable rule, and I have a constant. So I can just take the derivative of each piece and add here, subtract here. So I get y prime. So this one is going to be 2x. Then I have the derivative of a single variable, so that's just going to be 5. Remember, think of like 5, the slope of the line 5x is 5. And then here, this is a constant, and the derivative of a constant is 0. So this is my answer for y prime. I get 2x plus 5. Over here, it's already kind of nicely set up for us. So I just take the derivative of each piece. So here we get 4x cubed. Now I'm going to multiply and I'm going to get 9. So 9 halves x squared plus 4x plus the derivative of, remember there's like a 1 here, so we get 1, and the derivative of a constant is 0, so this is our answer for the derivative. Now, what I would do now we'll have another way, something called the chain rule that you can use, but on something like this, I would just multiply that out. So if you multiply 2x minus 3 times 2x minus 3, you can FOIL that, but if you remember, if you have a minus b quantity squared, you get a squared minus 2ab plus b squared. You'll use this so many times, you really should know that. So this is still y. So I square the first term, I get 4x squared. Multiply these in double, I get minus 12x. Square the last term, I get plus 9. So now I'm ready to find the derivative. So y prime is 8x minus 12. Remember, the derivative of a constant is 0. So on this next one, we need to kind of set it up better. So y equals 4x to the minus 1 minus 4x to the minus 2 plus 4x to the minus 3. Now I'm ready to find the derivative. So we get negative 4x to the minus 2. This is going to be plus 8x to the minus 3. This is going to be minus 12x to the minus 4. Then we're going to flip this back around. So we get negative 4 over x squared plus 8 over x cubed minus 12 over x to the 4th. All right, now on the next one, problems like this, you really want to simplify. Look for ways to simplify it first, because notice I have multiplication. We don't have a rule for that yet. But I can distribute right here and rewrite this function as 12. That's going to be 12x, square root of x times square root of x, just gives me x. And then here I'm going to have negative 18, and it's going to be 18 square root of x, but I'm going to write it as x to the 1/2. Because now notice I have it set up to use the power rule with the sum and quotient, or the sum and difference rule, kind of combining all those rules together. So we get f prime of x equals 12 minus half of 18 is 9, x to the minus 1/2. And if we wanted to write that only using positive exponents, we would have, I'll just flip that back underneath my square root, and so we get that answer. On part F, I am going to multiply this out. And on this one, yeah, it's kind of different there with, so this is what I do. I'm going to pause this just so I can kind of set it up and not use up time. So if I'm multiplying x squared minus x plus 1 times itself, a lot of times I will just kind of organize it in a box. So x, so you can see what I'm doing here. So x squared times x squared is x to the 4th, x squared times minus x. It's just a way to organize it. So then when I'm done, I can kind of go through and I'm going to rewrite this. I'm going to pull the 1/2 out front, and I'm going to have x to the 4th. I have minus 2x cubed plus 3x squared minus 2x plus 1. So that's kind of what I would do there. Then you don't have to multiply that through. Remember, this is just a constant. So when I do my derivative, I can just leave the 1/2 there. And we're going to have, now you apply the power rule to each piece. So we get 4x cubed minus 6x squared plus 6x minus 2. Then remember, the derivative of a constant is 0. And then because notice they're all divisible by 2, so we may as well fix that. So we get 2x cubed minus 3x squared plus 3x minus 1. So this is just a strategy to kind of help you organize if you have to multiply something out like that. So what I would do on this next one is I'm just going to rewrite this. So we're going to have 8x to the minus 1/2 minus 6x to the minus negative 1/3. And now just find the derivative. So we get negative 4x to the minus 3/2. That's when I multiply negative 1/3 times a negative 6, I get plus 2x to the minus 4/3. And then if I'm going to write it with positive exponents, I'll flip this to the denominator and flip this. Okay? Now, the strategy on this next one is when you have a fraction, when you have division, and you notice that it's a single variable in the denominator, it's not a sum or a difference, I can split this fraction apart and have 9x over x minus, and I'm going to change this to x to the 1/2 over x. So I'm going to do that. Then I'm going to simplify. So right away I see that these x's cancel. So I end up with y equals 9. And I can do something here too. If you remember the rules for exponents, when the bases are the same and you're dividing, you subtract the exponents. So 1/2 minus 1 is negative 1/2. So I have simplified my original equation to this, and I forgot my x. Okay, that's a little awkward. There we go. So now from there, I can find the derivative. So the derivative of a constant is 0. So then I have a positive 3/2 x to the minus 3/2. And we're going to have 3/2. I'm just going to put the x to the 3/2 in the denominator so it can be written as a positive exponent. All right, so that's just a trick to split apart the fraction if it's over. Now, you couldn't do this if you had a sum, like I can't do this here. On this one, I can't split it apart with a 2x and a 4 because this is a sum. This I could do. So here, what's the strategy going to be? Well, we are going to attempt to factor and see if we can simplify this first before we find the derivative. So if I factor this, this one here in the numerator, looks like we'll have a negative 8 and a positive 2. And here I can factor out a 2. So that conveniently cancels. So now I'm going to write this as 1/2 x minus 8. Or I may as well just write 1/2 x minus 4. Now notice this is still y. That's why it's important that you label things. I haven't even done the derivative yet. So now I'm ready to do the derivative, and I just get 1/2, and that's done. So I'm going to stop there, and we will just pick it up with the product rule another day. So just make sure that you have your notes filled out.